All right. So yeah, last method, fixed voltage method, it will kind of assume the voltage for the VMPP based on the season. Because again, when we think about it, winter brings us less irradiance, but a higher lower temperature. And then summer brings us a higher temperature, but also higher irradiance. So these are all factors that can give you a general MPP region again, if you just have a fixed voltage output. So with this in mind, we can really more or less understand the MPPT we have chosen, which is the Numera MPPT. As Mike has mentioned before in a previous knowledge share, Numera is a company that specializes in solar car manufacturing, and supplying. So they designed this MPPT, and the thing to note with this MPPT that's pretty important is that it uses the SPV 1020 MPPT-IC. And essentially, Numera just took the typical applications or the application notes and made their own MPPT. So, a future project that our team really wants to do is design this on our own and not have to pay Numera hundreds of dollars for these MPPTs. But we're going to use that for now. So what Numera has is that it has, it allows us to change the voltage reference output of the MPPT with certain configurable pots, but it mainly runs a perturb and observe algorithm. So as we talked about before, and this is in the data sheet, it does that kind of tracking where it edits the reference point so that it can keep trying to get closer to the maximum power point. The Numera MPPT, with a lot of other functions, it provides us a lot of protections as well. So it has an over voltage protection, over temperature protection, over current protection within the SPV 1020 and the MPPT design itself. So just to talk more about the protection mechanisms before I hand it off to Micah to really talk about how these MPPTs work and how we've been testing them. The overtemperature protection, the SPV 1020 itself will go into a pass-through mode when it's silicon, so the actual IC is greater than 150 C. Over voltage protection, it monitors the output voltage, and again, this diagram is the simplified block diagram, another really important thing to be looking at when you're looking at data sheets, to kind of understand the sense mechanisms and the comparisons it makes inside. Right, so over voltage protection must be less than 40 volts. It has an over current protection, which is measured based on the current going through the boost inductor, which is has to be, if it's greater than 5 amps, it'll go into OCP. And then it has an under voltage lock-in mode. And basically, this is when the voltage open circuit, the input voltage is less than voltage open circuit times a factor of 1.1. And so this just means it's not sufficient enough to provide any sort of kind of like efficiency trying to boost it. So it might as well just go and pass through. And it'll basically shut down all of the converter part of the SPV 1020. And I'll hand it over to Micah.
Cool. Yeah, so basically the Numera MPPTs are just a fancy boost converter that the SPV 1020 manages. There's 4 phases in this boost converter, basically 4 independent boost converters that are running with a synced phase, or a synced frequency and a phase offset. So the big question here would be why multiple phases? And with a boost converter, one thing that you have to remember is that as it charges and discharges the inductor, then the current to the output is going to rise and fall. That's what the top graph shows. So you're either going to be charging the output from the inductor or from the capacitor that's on the output. I think we went over boost converters in earlier tutorial. But yeah, basically we use transfer on the output. The energy is either coming from the stored energy in the inductor or from a capacitor. And during that transition, the voltage on the capacitor rises and falls because the inductor is either charging it or not charging it. So we had a changing voltage on the input. And the reason that's not good is because the solar panels require a fixed voltage reference to operate at their maximum power point, as we discussed. So we want that voltage to be as flat as possible. So we need that current to be as constant as possible. So the way that ST has designed the chip is that they have 4 boost converters that all run at the same frequency at offset phases, so that the average current going in, the average current going out is very even. You can see in the graph on the bottom, that's from their application note. They measured the currents going into and out of the module and the currents through each phase. So you can see the offset of each phase there, and the input and output current of the module is very even. So that's very important to keep it at the maximum power point as we're operating the MPPTs. And the other important thing to note is that that allows us to use less bulky input and output capacitors. Those in a typical boost converter are larger so that they can smooth out the voltage. But because we have this 4-phase topology, then we can use smaller input and output capacitors, and the board gets smaller and cheaper. Yeah, and there's a link to the datasheet and application note there if you ever want to reference it. They're also on Confluence. Yeah, so the other important part about these MPPTs is the diodes that are built into them. So there are 2 of them. One is called the blocking diode or pass-through mode diode, and the other is the bypass diode. And they're useful for various operating conditions of the solar panels. So with the bypass diode, it exists in case one of the solar panels gets shaded or gets cracked or something like that. Then it essentially removes that solar panel from the circuit and allows the rest of the circuit to keep operating. So if PV in is low enough, the under voltage lockout is tripped. In this case, this is the UVLO that controls the circuitry inside the IC and not the 1.1 times PV in that Ashmika mentioned. So that's a UVLO for the chip. It's about 6.5 volts. So if that UVLO gets tripped, then current can still flow through the rest of the string through the bypass diode. So we don't interrupt our whole solar system, we just lose one module instead of losing all 6. And the second diode is the blocking or through mode diode. And that allows the panels to still charge the battery even when the battery voltage is less than the panel voltage. Because these are boost converters, they can only step up the voltage. But if our battery is discharged or if our panel voltage is really high, then we won't be able to charge the battery with a boost converter. So they add a diode here that goes directly from PV in plus to PV out plus. And that basically determines when the DC-DC converter is not operating, there is still current that can flow from the panel to the batteries, which is exactly what we want, because that converter is not going to operate if the battery voltage is less than 1.1 times the input voltage. And that does happen at low voltages in our system. When the battery is like 20 to 30% state of charge, we'll be charging it through this blocking diode. Cool, you can go to the next slide. So the other important part about all this is testing it. I've heard it said that people are innocent until proven guilty. Your design is guilty until proven innocent, which is super important reason why you need to test it. So we need to validate all the individual parts, the panels, the MPPTs, the solar sense board, the ideal diodes, and everything in the circuit to make sure it operates as we expect. And that goes the same for any boards and any systems that we make. So one thing to note as we're testing the individual parts, when you're testing the MPPTs, they're expecting a very clean input power. By that, I mean very low voltage ripple. And solar panels are great at that, so are batteries, but DC power supplies are not. So if you're ever testing the MPPTs on the bench, then Namura recommends to add large capacitors on the input and output. And that will essentially it'll smooth out the voltage ripple of the bench power supplies and allow it to act more like a solar panel, but still not accurate. Yeah, when we were testing the MPPTs previously, we did run into some issues when we were not aware of this. Basically, the chip would occasionally lock out, go into undervoltage lockout mode and not recover. It would give random data on SPI or seemingly random data. So yeah, those are super important. When we connected to the solar panels, they worked really well. So yeah, just one thing to note there when we're actually testing it. So there's a few graphs in the test setup on the right side that I'll talk through now. We tested the MPPTs. We did a fair bit of testing in fall 2019, I think, end of fall 2019. Mm-hmm. Yeah, and we wanted to make sure that the MPPTs that we had chosen, the Namuras, would work. We had issues with them on MS12, and we didn't really know why we were having those issues. So we wanted to test them, make sure they work, throw every possible case at them, series and parallel arrangements, and basically try and get them to fail. And we weren't able to get them to fail, so that's good, but it's also weird that we couldn't get them to fail when they were failing earlier. So yeah, we're just expecting that they'll work as we tested them. But yeah, so we used MS12's trunk panel, and we set it up in the SDC. We got some high halogen floodlights. They're not ideal because they get really hot and they're not like crazy bright. Super bright LEDs would have been better, but they're pretty expensive. So yeah, this is just to get some amount of light on the panel so that we can actually get a valuable output. We were testing in winter and it was cold outside and we didn't want to prop up the array at 45 degrees to get any light from the sun, and it was often cloudy. So yeah, we opted for inside testing with lights.
We actually ended up doing that anyways. It's just that like winter and like the significance of a winter input power versus summer is crazy. So
yeah,
it was not worth it, but we tried anyway.
Yeah. So we connected, the MPPT is sitting underneath the panel there, and we connected a DC load. We operated it in constant voltage mode with SCPI commands, standard commands for programmable instruments. And that's programmed through Python. And we basically swept the voltage from 0 volts all the way up to 30 volts. And we measured the current that the panel was outputting at every stage. So that allowed us to generate an IV curve for the panel. So on the top, there's 3 areas that I've highlighted in those graphs. The green region is when the MPPT is operating in pass-through mode. And you can see the panel only in the MPPT graph. That first section looks exactly the same. So in that region, the current was flowing through that blocking diode, and it was charging, it was allowing current to pass through the DC load. And that's why those 2 sections look exactly the same, because the MPPT isn't doing anything. And then the orange section, the MPPT boost mode, that's when the MPPT algorithm kicks in and it starts boosting the voltage. So at that point, we were commanding a voltage that was at least 1.1 times the input voltage. And then you can see that it held a much flatter power curve in that area. So it kept the power output exactly at the maximum, and it decreased the input and output current accordingly to match that maximum power. And then once we reached the end of that section, it went into MPPT output over voltage mode, where it boosts up to a certain voltage on the output. And if it exceeds that, then the boost converter shuts down so that you don't damage any of your electronics on the other side that you're trying to charge. So in that mode, it just shuts off pretty much, and the output voltage and current both drop. And that would allow, if this was in the car, it would allow any extra charge to bleed off. If the batteries were slightly overcharged or there is extra capacitors on the bus from the motor controller regeneration, If they had dumped some charge back in and charged capacitors, then that would allow the charge from those capacitors to drain out and power the motors again, and then the voltage would fall and we'd move back into the MPPT maximum power point mode. So yeah, we can see that it drops, it operates as expected, and we can adjust that maximum output voltage point with a potentiometer that's on the Numira boards.
Cool. Thanks, Micah. That testing was actually really cool because we had used these Numira MPPTs in MS-12 actually. We never actually like fully characterized them as Micah did. So it is really interesting findings, and those graphs are really evident of the operation of the MPPT, which is amazing. Cool.
And we will need to do that exact same testing once everything is integrated on the car.
Yes. Okay, and now let's talk about SolarSense. So I guess a prelude. So MS-12 also used Numira MPPTs, except SolarSense was different in that there was more of a master-slave mechanism to the actual board. So what happened was that there was a MPPT sideboard that would be taking all of the sense measurements, and then it would be communicating over CAN to the master board. And this was because the intention was to make the entire system more modularized. So you could have the MPPTs and the board just sitting in like on the back of the trunk in a sequence, and then all feed into the SolarSense master boards. But we decided for MS-14, also because one thing to note is Solar never really worked functionally for a variety of reasons in MS-12, to redesign that completely. So what we have is the SolarSense board, and this board is what I think is it's really two boards combined into one. It has all of the MPPT inputs going into the board, and it literally connects them all of the outputs, MPPT outputs going into the SolarSense board, and it has all of those all the power flowing in series through the board, through the safety mechanisms, through the relay, and then through our battery connector that will provide charge to the batteries. In addition, this entire board also has voltage taps and communicates over SPI, the SPV 1020s, and the MPPTs themselves to collect sense measurements. So the architecture has really changed from MS-12. But the idea instead is that we don't really need the modularization they had before. We can simply have a board that does it all and have all the MPPTs sitting inside that solar enclosure instead of sitting near the array. They don't really need to be. So that is the idea with our new version. And this is the SolarSense board. It's also probably the biggest board we are manufacturing. So I think I will go through how it works, as well as like looking at the schematics on E365, so it makes more sense. So yeah, let's begin. So for the sense section, this diagram, actually let me present it, might be bigger, is a good block diagram of how all the sense really works. So you have all of the segments of the array, so the modules, as Catherine has explained, and they all connect to a singular MPPT. I'll explain the power path a bit more. Let's just focus on the sense mechanisms. But essentially, the MPPTs are going to interface with our board through SPI. So the SPV 1020s have a SPI, can be SPI slave devices. And so what we need to have is an isolator, a SPI isolator, I can talk about the isolation later, but essentially we need to have the SPI interface connect to our controller board. Other things we get from the MPPTs, or actually from the array itself, is the temperature. So that's because we put onboard panel thermistors, and we connect them to our SolarSense board, which will have an ADC conversion of the thermistor voltage divider. We also measure the output voltage from each MPPT, and And finally, the last like real sense measurement is the current sense from the output of all the MPPTs. So the current that the entire section of the array is providing. Let me go. So I kind of mentioned all the types of sense, but just to reiterate, we have the array module voltage we measured, module temperature, module current, and then this comes from our SPI communication. Also comes from our SPI communication. We have thermistors for this one. We measure the MPPT output voltage. We have our own mechanism in place for that. And then we measure the MPPT series current output. That's with Hall effect sensors. We measure it ourselves. And then finally, MPPT also gives us temperature faults. It doesn't give us the temperature of the silicon, but it'll give us a fault indication when the temperature limits are surpassed. So the first thing that is notable is the SPI interface with the SPU 1020. We get a lot of measurements through SPI, as well as are basically able to interface with the IC, ask it to reset through SPI communication. And if you're unfamiliar with SPI, it's a low-speed protocol that is based upon the usage of a clock, a master in, slave out, and a master out, slave in lines. It also has a slave select line, which is basically a way for it to determine which device on its bus it's talking to. So like I2C, it has a clock, and a master out slave in means that the master is sending data based on the clock edges to the slave, and then master in slave out is when the slave is responding based on another sequence of the clock. So you can kind of see from this diagram. So what we really get from the SPB 1020 over SPI is the input V sense, input current sense that the module has to already be measuring again to have the maximum power point tracking. It gives us our faults, and we're able to send a reset, like I mentioned. And now I can kind of walk through the schematics and how it's really implemented. So we have our SPI interface sheet. And what we have here are digital isolators. These are probably one of the more expensive ICs we purchase. I think they're about $30 each. But what they do, they have multi functions. So when we look at the entire board, we have to have the controller board interface in SPI with the each MPPT. But the problem is, and I'll talk about the isolation right now, each MPPT is giving us a reference, or is outputting like up to around like 30 volts, right? So the problem with having the SPI interface based off of the ground that we use for signals is that if we do that, an MPPT that's providing, even the second one, its ground reference will be a 60 volt drop, and all the components that are referenced to, for some reason, in this case, the signal ground, or the ground that our controller board provides, will be suffer because they're not 60 volts tolerant. And so we see that we really need isolation in the grounds, and that for every MPPT, we need a separate ground. So that's where you kind of see this layout of all of these, like, they look like ducks, but all of these sections that are referenced to the same ground and are isolated from each other. Two MPPTs can't share the same ground because, for example, if they were, it would still be like a 60 volt difference or a really high voltage difference, which would not allow it, which will damage the components because we would have to be dealing for different tolerances for every single segment of the MPPTs. And again, if we look at the power path, each MPPT is a voltage source that's connected in series. So this ground is a reference to this ground of basically the output of this MPPT. And so what's necessary is for our SPI communication to not be referenced to the same ground for different sections of the power path. So while the controller board is referenced off of this huge red plane ground, which is now highlighted, my gosh, that's so cool. It does that. Okay. This ground is a different reference. And so what we need is an isolator. And now the special thing about these isolators, the ISO W SPI isolators, is that they also provide output power. So while we are because of the way that SPI works, this isolator it has it's not bidirectional. The communication for master out slave in, clock, and chip select, which is also called slave select, all go in the direction from controller board to MPPT, and other way for MISO. But what this really does is it gives us a 3v3 reference, which is needed for the communication based on the new ground, which is really useful because it's basically able to provide us power on the 3v3. And we use this 3v3 power output that the ISO W provides us for a variety of other functions for the side of the MPPTs that are isolated from the digital ground. And for example, the ADCs that we have sitting on the side of the MPPT grounds use the 3-volt reference to power on. So that's kind of like what this IC is really meant for and how it's so useful and why it's so expensive. But yeah, it provides us that isolation that we really need. And then the last thing that's relevant to the SPI communication is that we have this multiplexer. So the real reason for it is that there's 6 MPPTs per solar sense board, and they have each chip select has to be connected to a different GPIO. And the way for us to save on GPIO pins is for us to just have a multiplexer, so we only use 3 and can control the output of 6 slave selects or chip selects. So that's just how this has been formatted to save pins on our controller board. Another thing I might not have mentioned, but hopefully will make things a bit clear. Like Catherine mentioned, there are 11 modules. Each solar sense board has input of 6 modules, so there has to be 2. And what happens is that the output of 6 in series is paralleled with the output of 5 in series. So that provides us almost double the power output as if we were to only have 1 solar sense board. And that's just like how that architecture works. So we talked about SPI. Now let's talk about the voltage sense that the solar sense part of this board really measures. Voltage sense it starts off as taps from the connectors with the output of the MPPTs. And as you can see, this section of the schematic also has the power path. Everything connecting series. We'll look at this later. But we have it so that the MPPT input taps, they go through a voltage divider and then through a buffer. So basically, it needs to go through all this because, again, this reference is at like 30 volts or whatever the boosted voltage of the output of the MPPT is. For our controller board not to be damaged by getting that input, we need to divide it down so that it's under 3v3 reference, and then have this buffer op amp so that it just helps with the power integrity. And then it goes out and goes to the ADC page. Oh, sorry. First it goes to the vSense ICE. No, that was the ADC page. My bad. ADC page. So now that we have an analog reference for what the output voltage is, it goes through an ADC, and this ADC, or these ADCs all sit and have to sit on the isolated voltage sides of the MPPTs. And then what happens is that they reference the 3v3 again from the ISOW module, and then they communicate over I2C. They each have a different slave address, and that's just configurable by the address pins. So this diagram that can't show up is that all the addresses. So now that we have this ADC, which converts the analog voltage to digital communication, we need, again, another isolator for this I2C, because again, it's being referenced to the MPPT voltage, not the controller board ground reference. So I2C interface for vSense exists here. And again, there's 4 devices, or sorry, 6 devices. And they all have pull-up. You'll notice that they all have pull-up resistors on the output of each, on the input of each I2C isolator. And that's because each MPPT section, again, is on the other side of the isolator is being isolated from each other. So we need the pull-ups in all of these cases. But when they are all referenced to the ground reference, we only need 1 pull-up because all the buses are connected directly. 1 set of pull-ups, which is just kind of like how I2C works and how this isolation factors in. And then finally, the SDA and SCL lines are going to our controller board over here. Cool. So that kind of describes the same thing. And then we have our temperature sense, which we use PT100 thermistors that actually were provided to us by or with the array, several of them at least, and they're pasted or stuck or mounted, sorry, to the underneath of each array module. What we do in terms of schematics is we simply have them be an input through the connector and put our own voltage divider that'll go into the controller board's ADC GPIO pins. So it's very, like, this uses 6 pins, but we have the space, so might as well. And we measure each segment. And then we have our final sense, which is our current sense, or final sense implemented hardware, our current sense, which is our Hall effect sensor. Hall effect sensors are a way to measure current based on the intensity of the magnetic field. That's what they do. And instead of a shunt current sense as we've seen before, we've also seen Hall effects. They are an isolated way to measure the current. So the Hall effect we use is an open loop Hall effect, which essentially means it doesn't have as much of fast response and high linearity or low temperature drift as closed loop Hall effects do, but it doesn't lose feedback like closed loop Hall effect sensor, and it's cheaper. We don't need the accuracy that closed loop sensors provide, so we use an open loop. And finally, it's bidirectional. So the layout of this sensor is to be in the power path of the board. So if all of the MPPTs are in series over here, the Hall effect sensor lives right here, and it's basically, sorry, here, and it's basically able to not interfere with the circuit, but give us an analog reference for what the current is, which then will go into another ADC that will that sits here and then interfaces over I2C again with the controller board, but on a different bus than the voltage sense. So something important to note here is that the reason we want a bidirectional switch is because we expect the current to go through high voltage high, basically output of the MPPTs, into the Hall effect and out. But in the case that somehow the battery voltage or somehow the current is reversed so that it goes the other way, we want to be able to sense that there's a fault and the current is going the other way. And I'll get into how that can happen, like right after power path talk. But yeah, that's essentially a Hall effect sensor. So now we're talking about the power path. This diagram is not the most accurate, but it gives you a good idea of what the flow of current really is. You connect the output positive terminal of an MPPT to the negative of the next one in series. And that's how these numeric MPPTs work. And their input is the section of the arrays. So the power path, again, is 6 MPPTs in series that go into an output, go into our ideal diode, a relay, and then enter our high voltage loop to charge the batteries. And the same goes for the 5 MPPTs in parallel with the 6 ones. So now what we really need for the power path are safety mechanisms, which include our relay, fuse, and ideal diode. Because again, this is a lot of power that's going through the system. And that's what we're going to talk about next. So the first thing we could talk about is the ideal diode. This is a component that will essentially operate as the name implies, a diode. It will not break down in reverse. It will prevent a voltage on the output or on the cathode of the diode from inducing a reverse bias current. So the reason this is especially important is because in the case that the battery pack voltage is a higher reference than what the array can provide, the current the battery will try to discharge into the array. And that's a problem because not only will it damage everything in its path as well as the array, we never want the current to be going from battery, or we never want to discharge from the battery to anything solar related. So what the ideal diode does is it's our safety mechanism. It basically makes sure that if for some reason the battery voltage is higher potential than our array potential, and somehow the relay is still closed, it is the way to make sure that we are not discharging into the array. And so what we use for this is an LTC 4359. Its application diagram is something we really referenced, and it's implemented in a way to withstand 200 volts of reference, because again, this is a high voltage system, and this IC is not 200 volts tolerant. So what we get, and I made an LTC SPICE simulation for this because it is an LT part, so I couldn't help myself, but it basically, how it works, and I can expand this, is, okay, so what we have here is a Zener diode that's referenced to 12 volts. What happens is that because of this 12 volt reference Zener diode, the IC is really only referenced to a VSS of 12 volts. And by that, I mean, if this is like 100 volts on the input over here, VSS is only 12 volts less than 100. And so it's not referenced to 200 volts. The rest of the voltage drops across R1 over here, our 200K resistor. So that's one reason for this Zener diode. How this actually works and how it's able to turn on this N-channel MOSFET is that when this MOSFET, its gate is a depletion mode N-channel MOSFET, by the way. So that means for it to turn on, the gate has to be at least -3 volts reference with respect to source, which is where the arrow always is connected to, by the way. So when that happens, that means that for the input here, let's just say it's 100 volts. What's happening over here is that we have a 15 volts Zener diode. And so what that does for us is, because it's 15 volts and not 12 volts, and remember the NFET has to usually have, or depletion mode NFET usually has to have a -3 reference over here with respect to this one. This 15 volt NFET makes the reference here 3 volts higher than over here, and this turns on the FET. And why this is important is this is a way for us to have like a secure way of measuring the output voltage and bringing it back to our LTC 4359. Because again, this chip will determine if it's safe to close this NFET so current can pass, but only if the reference here is greater than the reference here. This being the battery side and this being the array side. So that's what the gate pin is for over here. And what it'll do is it'll pulse on the gate pin and turn it on when it sees that difference in voltage, in and out being reference points for it to figure out what the voltage is on either side. So that's the main function of this device. And this is going to stop again, but I'm going to try to show the simulation anyways. So for this simulation, we have